In this lecture, we will discuss about a special form in which a matrix can be basically a similar form in which a matrix can be represented. This will this is popularly known as the Jordan form of representation, and we'll be doing this particularly for those matrices whose all the eigenvalues are real. We will discuss Jordan forms for those n cross n real matrices whose all eigenvalues are real. We'll focus only on those matrices. Okay, so let's say that A is a n cross n real matrix. Okay, where let's say that A is a 3 cross 3 real matrix. Lambda equal to, let's say, alpha is the eigenvalue of A, and m1 is 3. Okay, so let's say that this is the situation that we are actually in. Now, what are the possible values of geometric multiplicity? It is 1, 2 or 3. So when m1 bar is 1, you have a vector which is GV of grade 2 and grade 3. Okay, so this indicates that you have one OEB. When m1 bar is 2, we have one GV of grade 2, which can come from either of the ordinary eigenvectors or possibly a linear combination of the ordinary eigenvectors as well. When m1 bar is 3, then you have no generalized eigenvectors of grade higher than 1. Okay, the generalized eigenvector definition that I had said was what? That A minus lambda I k v is equal to 0 and A minus lambda I k minus 1 v is not equal to 0. Okay, then v is a GV of grade k corresponding to the eigenvalue lambda of the matrix A. Okay, so I said that this is for k equal to 2 and more, but actually for k equal to 1, when k is equal to 1, this is termed as OEB. Okay, so this basically when k is equal to 1, we have the definition of a b equal to lambda. Okay, that is what I just wanted to clarify. Okay, now coming back to our discussion here. When M1 bar is 1, GV, there are two GVs, one of grade 2 and one grade 3. When M1 bar is 2, there is one GV of grade 2. It can come from either of the sorry, you have one OEB here. You have one OEB there. You have one GV of grade 2 and two OEBs, and here you have no GV but three OEBs for when M1 bar is equal to 3. When M1 bar is equal to 2, this GV can come from either of the ordinary eigenvectors or a linear combination of these ordinary eigenvectors. Okay. Okay. Now, so for this case, let's say we'll first see for M1 bar equal to 1. When M1 bar equal to 1, let's say that A V1 is equal to lambda V1. Okay. A V2, where so V1 is the OEV, V2 is the GV of grade 2, V3 is the GV of grade 3. So AV2 is what? Lambda V2 plus V1. What is AV3? Since AV3 is of grade 3, so this has to be 0. It indicates that A minus lambda I square multiplied by A minus lambda y V3 has to be 0. If I set this to be equal to V2, then my job would be done. So what I have is AV3 is equal to lambda V3 plus V2, and A is a matrix that represents possibly some linear transform. Okay, and V1, V2, V3 are the eigenvectors, and I had said, as I had said earlier, that V1, V2, V3 are linearly independent. So V1, V2, V3 basically form the basis of a vector space. In this case, this would be R3. Okay. Now, when A acts on V1, you get lambda V1. When A acts on V2, you get V1 plus lambda V2. And when A acts on V3, you get V2 plus lambda V3. So the matrix representation of the linear transformation represented by A with respect to the basis V3. Or rather, so I can write this 3 equation as A multiplied by V1, V2, V3 is equal to lambda times V1, sorry, equal to V1, V2, V3 multiplied by, so lambda times V1, 0 times V2, 0 times V3, then you have 1 times V1, lambda times V2, 0 times V3, then you have 0, 1, and lambda. Right. So so what is A here? So you can see this A as the matrix A is the matrix representation of a linear transform on the vector space R3 with respect to the basis 1 0 0 0 1 0 and 0 0 1 with respect to this basis. Jordan form of the matrix A can be thought as the matrix representation of the same linear transformation with respect to the basis v1, v2, v3. Okay. So what you essentially have is, so if you remember that we had a basis x and a basis y for a vector space V, and then a matrix representation as ax and ay, and we saw that this is nothing but e. So we basically had this relationship, if you remember, px inverse ax px from the similarity transformation, right? Or basically this is something like this. So this A and that A are different. Okay. Well, basically in that A, that is a matrix where I have dropped the basis sign associated with the basis and the square bracket thing that I have dropped in the notation. Right. So this is what we had seen as a part of the singularity transformation for two different bases. Now here, this 1 0 0 0 1 0 and 0 0 1, these three vectors can be considered as the basis x, and the eigenvectors here can be considered as the basis y. So what to have as a relationship here is something of this form, where px is nothing but the eigenvectors. Okay. So the ay here is the Jordan form. Ay here is the Jordan form. So in the Jordan form, it is basically a matrix which contains the eigenvalues in the diagonal. Okay. Or rather, I should put it that it is a matrix which has, it is a block diagonal matrix where each block is something known as the Jordan block. Now, what is a Jordan block? I'm seeing a lot of things, so let me put it down. Jordan form of a matrix is a block diagonal matrix, okay, of the form, let's say J1, J2 till Jm, and these are all zeros, where J1, J2, Jn are the Jordan blocks. Okay. Now each Jordan block corresponds to a particular eigenvalue. Okay. The structure of a Jordan block is this. In a Jordan block, corresponding to an eigenvalue, the diagonal has the eigenvalue and the super diagonal, basically the diagonal just above the main diagonal. Okay, the main diagonal has the eigenvalue as its entries, and the super diagonal is 1, all ones. Okay, for example, this is the Jordan block. Okay, so this is the main diagonal, and this we call as the super diagonal. Okay, so this is the Jordan block. So what we just saw is, in the example where A was a 3 cross 3 matrix with the eigenvalue to be alpha and the algebraic multiplicity to be 3, and the geometric multiplicity was 1, the Jordan block came out to be of the form right. Let's look back. This is the Jordan form. Right. This is what we have here. This is the Jordan form. Now this Jordan form has only one Jordan block, which is the entire matrix itself. Now let's look for when M1 bar is 2. In that case, you have two ordinary eigenvectors. So that means, let's say AV1 is lambda V1, and I label that as the third vector to be the ordinary eigenvector. Okay. Now the generalized eigenvector can be generated either from V1 or from V3 or from a linear combination of both. If it is generated from V1, then it cannot be generated from V3. If it is generated from V3, then it cannot be generated from V1. Okay. And sometimes the generalized eigenvector needs to be generated from the linear combination of V1 and V3 because it cannot be generated from either of them. Okay, but the algebraic multiplicity and the geometric multiplicity together are indicating to the fact that there has to be one ordinary eigenvector. Okay, so here we'll assume that the ordinary eigenvector is being generated using V1. So V1, V3 are the ordinary eigenvectors, and V2 is the generalized eigenvector of grade 2, such that I have a V2 to be lambda V2 plus V1. So if I put this as A on V1, V2, V3, what I get is V1, V2, V3 multiplied with lambda 0, 0, 1, lambda 0, and then 0, 0, lambda. Okay. So the Jordan form J is this, and how many Jordan blocks that you have got? You have got 2 Jordan blocks. So this is one Jordan block, this is another Jordan block. Okay, Jordan block corresponding to the eigenvalue lambda, and again Jordan block corresponding to the same eigenvalue lambda. Notice that the number of Jordan blocks associated with the eigenvalue is exactly equal to the geometric multiplicity of the eigenvalue. Okay, number of Jordan blocks associated with an eigenvalue is equal to the geometric multiplicity of the eigenvalue. There is another thing known as the index. The index of an eigenvalue is the largest order of the Jordan blocks associated with the eigenvalue. For example, in the first case, when the geometric multiplicity was 1, that indicates that you will have only one Jordan block corresponding to the eigenvalue lambda, and the index of this eigenvalue is 3. Similarly, in the second case, when the geometric multiplicity of the eigenvalue is 2, indicates that there are 2 Jordan blocks, and the index of the eigenvalue is 2, because the largest order of the Jordan block is 2 in this case, that is associated with the eigenvalue. It is just a mere coincidence that when m is equal to 2, the number of Jordan block is 2, and it so turns out that the index of the eigenvalue is also 2. Okay, the index of the eigenvalue and the number of Jordan blocks need not be the same. Okay. So for M1 bar, we had one Jordan block, but index 3. For M1 bar equal to 2, you have two Jordan blocks with the index of the eigenvalue being 2. When M1 bar is 3, you'll have 3 OEVs indicating AV1 equal to lambda V1, AV2 equal to lambda V2, AV3 equal to lambda V3. Okay, so what you have is A, V1, V2, V3 is equal to this particular expression, V1, V2, V3 multiplied by this Jordan block. So here essentially you have 3 Jordan blocks. Okay, each Jordan block is of size 1. So index we will represent by let mi tilde. Okay, so here the index is 2, here the index is 1, and the last example here the index is 3. In the last example the index is 1. To get a better picture of this Jordan block, let us take another example. So suppose that A is a 4 cross 4 real matrix. The eigenvalue that A has is this, with the algebraic multiplicity being 4. Okay, algebraic multiplicity being 4. The possible geometric multiplicities are 1, 2, 3 or 4. Okay, so it means it might have 1 OEV, 2 OEVs, 3 OEVs or 4 OEVs. When M1 bar is 1, that is 1 OEV, that means number of Jordan block is 1, and the Jordan form would be of this form. One lambda 0 and 0 0 1 lambda. Jordan block would be of this form, indicating that the index is 4. Okay, so you have basically 1 OEV and 3 GEVs. The grades are 2, 3 and 4. When you have M1 bar to be equal to 2, basically the geometric multiplicity is 2, then you have 2 OEVs, okay, and 2 GEVs. Now these 2 GEVs may be of grade 2 and 3 arising from only one ordinary eigenvector, or both of them can be of grade 2 arising from each arising from one eigenvector. Okay, so this is from one eigenvector, this is from another eigenvector. Here in this case this is arising from just one eigenvector. Okay, so in this case the Jordan form would look like this: 1 lambda 0, 0 1 lambda, and this. So if you demark it, this is what you have. There are two Jordan blocks. Okay, so you have two Jordan blocks, and the M1 here is 3. I'll correct this to 1. In this case, the Jordan block would look something like this. This is the Jordan form that we'll have, and there are two Jordan blocks. Now, the number of Jordan blocks remains fixed, but what you see here, that the index of the eigenvalue is 2. When M1 bar is 3, you have 3 OEVs and 1 GEV, and this GEV will be of grade 2, which can come up from either of the OEVs. Okay, will come from either of the OEVs. So this indicates that the Jordan block is going to be of this form. Okay, so how many Jordan blocks we see? Here we see that there are 3 Jordan blocks. Okay, so 3 OEVs means that there are 3 Jordan blocks, but the index in this case is going to be 2. The last case is M1 bar equal to 4, which means there have to be 4 OEVs and no GEV. So in this case, the Jordan block is just a diagonal. The Jordan form is just a diagonal. And how many Jordan blocks do we have? We essentially have 4 Jordan blocks. Okay, so 4 OEVs. Each Jordan block corresponds to a OEV, and the index in this case is 1. Okay, so in both the examples I have taken matrices, assume that all the eigenvalues are same. You can possibly have matrices, let's say, of this form, where one eigenvalue is this with let's say algebraic multiplicity being 3, and the other eigenvalue is this with the multiplicity being, it can be 1. Okay, sum of the algebraic multiplicities of all the eigenvalues is always equal to the order of the matrix that is under consideration. Okay, I'll need this. Sum of the algebraic multiplicity of all eigenvalues of a matrix is equal to the order of the matrix. Okay, remember this. Okay, so in this particular example, let's say that the M1 bar uh, is 2, and of course M2 bar has only one possibility, which is 1. Then the Jordan form might possibly look like the following. M1 bar is 2, which means for the eigenvalue alpha, there would be 2 Jordan blocks. Which is of this form. And then you have the other eigenvalue, which is beta. So the Jordan blocks that you have for alpha are these two, and the Jordan block that you have for beta is this. So what you have here is index of alpha is 2 and the index of beta is 1. Here you have 2 Jordan blocks. Here you have 1 Jordan block in the Jordan form. We'll stop here. Thank you.